And the good thing is that, so I brought up these slides, which is sort of an update of the useR, the tutorial I gave in useR in Brussels last year, which is exactly a year ago. So you could argue there not so much has changed, and that was indeed most of it was sort of developed in the first year, and a lot of things that changed were sort of really low-level changes or things that I added or something like that. So yeah, we will sort of look at more detail into simple features, and I already gave a bit of an introduction to what these are yesterday, and I will go through through that more slowly and with more sort of jumping to links to external material. In any case, if there is any moment where where you feel that my voice is dropping, yeah, so I start, after an hour or so, I start murmuring. My wife always complains. So raise your hand or start shouting at me that I have to speak up and so on. And anytime you hear something where you think, hey, I can't connect to that, here's a concept or a word or an idea that I can't grasp, then please raise your hands and ask, yes, because we have time, yes. That, of course, if everyone does that, we get halfway, but it's better to do that than sort of have me bulldoze through all these, all these slides and material and so on. We had an interesting discussion during breakfast that R and package versions, this has nothing to do with simple features. You occasionally, when you install a package like SF or so on R, you will see, hey, this package doesn't work with your R version. It was compiled for R350, and you are running a much older version of R, yes? And it may even give an error, like it won't work or so, or it might give a warning and you might be worried. In any case, if you work with binary packages from cron, binary packages are not, as you see, they're not sort of offered for all historic R versions, yes? They are offered for the current R version. So the R community essentially assumes that, if you have a problem and you want to raise your hand, that what you made sure is that you're using the released R version. Yes, that's the current R version. Yes, that is the first assumption. So if you then come up, oh, look what I did, and you see R 3.2.0, then everyone stops looking, yes, and says, okay, install current R, try again, and then ask again, right? That is kind of the assumption. Some people find that there are other software environments where people get attached to, certain versions of like ArcGIS 9 point something or something like that. Yeah. So, and because it worked, yeah, and we don't want to change it into something that doesn't work. Yeah, that's not the case here. The newer R version is better than the older R version. You just do it. Yeah, there is no doubt about it. There has been testing going on. So that has nothing to do. So there is a little short. So okay, here is this document. This is an HTML document that I sort of gave a link on the Google Plus group. So this is parsed from R markdown, and R markdown is something like IPython or Jupyter Notebook or something like that. But then for R. It's markdown in R and sort of processes, and I'll see how you can get there, how you can create this document first. Yeah, so I said on the end of the table of contents, you see the R markdown sources of the tutorial is found here. Do I, by the way, have to enlarge my font here? Yes.
What do you think about the Microsoft R version?
I have no clue. I recently read some blog about people or some comments on our studio community discussion things about Microsoft R, and they have a couple of features. It's MKL libraries, fast sort of parallel matrix libraries. Yeah, so if you do linear algebra all the time and work on a Windows machine, go for it. Yes, if it buys you time and uses your 4 processors instead of 1, then go for it. There are also other matrix routines that you can link, that I can link, so the whatever the OpenBLAS or so, that or Atlas or something that do that too. Yeah, I don't.
So it's optimized for computing. I use, by the way, the Microsoft R constantly, and it's not really made by Microsoft. It was made by R Evolution, but then Microsoft bought the R Evolution. So it's like the GitHub. It's not, GitHub wasn't made by Microsoft. It was just bought by Microsoft. So so it's optimized for computing, and they optimize it with these MLK libraries. And so if you need to do heavy processing, then it's a bit easier to install. But there are also installations of R with BLAS. It's just you have to run a bit more code.
You're repeating me, Tom.
Yeah.
So I was here, and I was going to explain you how to sort of start with this R markdown file. So the source of this whole document is found here. If I click here, then I get this file, which is basically the source file of everything. And now I have to say, this is a bit odd, but I have to save it. So tutorial.rmd, let's save it in TMP. And then I can go there and open the tutorial.rmd, and that automatically starts our studio with this RMD file. Yes, that is now opened here. Yes, and if I then have this thing in RStudio and I click knit, then knit means that the whole thing is being compiled into an HTML. That means all the markdown is being formatted, and all the R things are being I see, that doesn't work, yeah, because it wants to, okay, yeah, so it needs a PNG file to include here, so it doesn't sort of automatically run, but you can go to this, sort of, if you want to sort of have these, the sources to run this thing, then you need to go to the GitHub repo, which is here. Which is here, and which has these files, which has the things in it, right? So you need to have then this image in it, or you can clone this library and then start the tutorial there. Yes. And this is basically where I was working on. This is the original one I was working on. So when you have it in RStudio, you can knit the whole thing, and it's being run, and all the R chunks are being processed, and the output is being inserted into the document, and the whole document is being created. So now I just recreated the whole HTML page, and then I can say open in browser, and then you see. Here it is. Yeah, here is my tutorial.html, yeah, which I just created. So you can get there. Yeah. So as an alternative to copy and pasting all the R chunks in your console, which also works. Yeah, which is also fine. Yeah, but you can also work from the sources. But of course, it is like a big program, and it doesn't sort of give you any insights or so. Yeah, we're today here, we're for insights, so let's do things step by step. There is a little section on the short history of handling spatial data in R that Roger sort of brought to you extensively yesterday, and this is pretty much incorrect. Here is this view of R packages that we saw yesterday, and then there is the simple feature access in R, which is package SF. And so package SF deals with this ISO standard that has a link here. So this is the link to the OpenGeoSpatial consortium page of the standards documents. These pages always look like this. There's 3 parts, and the part 1, common architecture, is the most interesting one. And you can see here that there is a version 1.2.1 of OpenGIS implementation specification for geographic information, simple feature access part 1 common architecture. Yeah, this is a document from 2006, as you can see. The 06 stands for 2006. These are older versions that you're not supposed to read, right? So you can look at that. So the document is now loaded here. We have the document here, and we have the standards document. Yeah, so this is, so to speak, the ISO standard. It's not the ISO standard, as I said. The ISO standard is 150 Swiss francs, but this is basically the same, the document with the same contents that went into being the ISO standard. And you can see here a lot of definitions, but one of the nice graphs is the overview graph of the simple features as we know them, and that kind of gives you the geometry class hierarchy of these things. Yeah, and this is one of these kind of UML diagrams that I never learned how to read. So I always, despise my students who submit bachelor or master's thesis with UML diagrams. I say, oh no, a UML diagram. But it's kind of not so much rocket science. You see a couple of things that you won't really recognize as simple features like surface, but you also see a couple of things that you do recognize, like line string we found, polygon we found, but we also found multi-polygon here, multi-line string, and it simply says that something like a line string is composed of 2 or more points. Yeah, 2 ... means line string needs to have 2 points or more. Yes, and there's even more constraint that the 2 points shouldn't coincide. Otherwise, it's not a line. And then a line string, yes, goes into a multi-line string. Yeah, multi-line string has to have 0 or more line strings, interestingly. So if we have a multi-line string with 0 line strings, it will be an empty multi-line string. Yeah. And so then we have line, linear ring goes into polygon, triangle and tin. So there are a couple of exotic things. And we have sort of the basic thing, point, line string, polygon, here, these 3. And then we have here multi-polygon, multi-line string, and multi-point. They are the let's say the multi-guys. Yeah? And then a collection of anything is called a geometry collection. And then there is the superclass. Yeah, this is all sort of about classes and about types. The superclass here is geometry. Yeah, so you can see geometry as unspecified anything. Yeah, that is there. And then geometry has reference systems, and there can also be, like for the M, as I said, for the M coordinate, a measurement reference system. And then there's a lot of text. So the whole document is, as you can see, is 93 pages. Some of it is worth reading. Yeah, it's not so written so bad. As I said yesterday, feature is an abstraction of a real-world phenomena, and simple features are basically things with geometries where the geometry is simple, meaning they're sort of points connected by straight lines. There are 7 types that we just mentioned. We mentioned the 7. There are 10 others. And I yesterday visited this link that goes to the Wikipedia site of the simple features. And there when I created these slides, it went up to 17, yeah, up to the triangle. And to my big shock, I noticed yesterday that suddenly there are like 10 more or so, circle, geodesic string. So some people are going on with creating geometry types, yes, and anything after 17 is definitely not mentioned in this document, but is apparently used by some people. But you can see that a lot of these things are about curves. Yeah, that anything beyond 7, also beyond the geometry collection, basically 1 to 7 are simple things. Yeah, the line strings, polygon, multipoint. Point, line string, polygon, multi-point, multi-line string, multi-polygon. They're simple things. And then we get something like a circular string. Yeah, so that is kind of a circle arc. Yeah, so that is something that's defined, let's say, by 3 points. Through 3 points, we can pull a circle arc, I think, but it's not a straight line. Yeah, so it's not simple. So in that sense, you think, why does this fall in the simple feature chapter? Yeah. But this is all historical, and it's not so interesting because you will rarely run into these things. Yeah, and when you run into these things, the first thing you do is make them sort of line strings, sort of approximate them by piecewise line strings, and that's what SF also can do, so that you can plot them. Yeah, because why would you have circles, parametric circles? And a couple of other complex types are there as well. Yeah, so as we mentioned yesterday, we start as F. We can start package as F after you installed it. That links to geos, gdal, proj, and liblwgeom. And then we can do basic stuff, right? So for instance, create a point. Yeah, that would be one of the basic things. So we have these functions in SF, like stPoint, and they are really sort of functions there. We can see them as constructor functions. So they take two coordinates and they create a point out of that. Yeah, so as a simple feature. But they're really sort of toy functions to work with, right? They are not, let's say, they're not functions to do serious stuff with or so, right? They are kind of there so that you can play around with these things. The more typical use case is that you start your analysis by reading some data from somewhere, from whatever it is, a shapefile, a geo package, a spatial database, or a CSV file with point coordinates and columns or something like that. I mentioned on the Wikipedia site there was a link to the well-known binary, sort of representations of things where it's explained how this encoding works, and in a pretty sort of reasonably understandable way. And this is basically, here is a point sort of represented as a sequence of bytes, where bytes are sort of written as hexadecimal, so two-digit codes. And we see the same thing if we do that with SF. If we say STS binary, then we get a raw vector. A raw vector is basically an R structure. It's a special vector in R for collection of bytes. Yeah, so if you have binary information, if you want to read like a JPEG, just the bytes, yeah, the sort of the raw as the file is, but then have it in memory and find out what is the byte value at position 1000. You can read the thing into a raw vector, and you can then query it, right? So so this is the conversion to a byte, and this is simply a way of printing this, so you can see that this is similar to what happens here, except that this is sort of reversed, that this has reverse byte order. You can see this is big endian, where most computers now are little endian. So then you see that, for instance, the second number is a 4-byte int, is reversed, is 1000, and here it's 0001. Yeah, so the byte order is reversed. Yeah, you have these byte order things. Yeah, byte order is one of these extremely cool programming concepts that, when you never run into it, praise yourself lucky. I will not talk about it further. The thing is that we have this binary thing here, which is just bytes, a byte string. Yeah, so that is the byte string that also goes into your PostGIS database, or that comes from your PostGIS database. And we can sort of convert it back and say, okay, if we have this binary thing, then convert it back to an SFC, and simple feature object, and we see again that it's a 0.24. Yeah, so we made a round trip to binary and back to an R object. Right, so this was about simple feature access, so this is about representation. Access means representation, getting them in and out of your system, as well as doing things with them. Access also means analysis, analyzing them, finding out, learning about them, finding out, for instance, what the dimension is of a point. You can see here that this point geometry has dimension 0, and that we can do an intersection, and we do here an intersection of the point with itself, and we get a true out of that, yeah, because the point coincides with itself. So yes, this is true. And then you can, if you want to sort of dive deeper into how this is represented in R, then you can use the str function. Str kind of prints the structure of objects. Yeah, so a lot of, if you create something and then you type object, so if I create the point and say, oh, I have to enlarge my. So if I create this point to 4, then if I just type the object, it's printed, but as you can see, it's printed as well-known text. Yeah, so there is a print method for these objects. So this is not what it is. This is not how it's represented. Yeah, so the str sort of tells you how it's represented. It says it's an object in a very short way. It says an object of class xy. It actually has more class attributes, and is a numerical vector of length 2 with values 2 and 4. Yeah? So that's in it. Yeah, so it's really simple. We also looked at list columns yesterday, and this is particularly interesting in the context of the whole tidyverse and what people are doing in tidyverse and make kind of assumptions they make. And so the storage model for these data is really that we store simple features, geometries, as list elements in a list column, and that we have a single column, so to speak, a variable in your data frame or in your tibble to represent all these things. Yes, and the storage form is very simple. It's a vector for point. It's a matrix for point sets, multi-point or line string. It's a list of matrices for sets of point sets, multi-line string, polygon. And it's a list of lists of matrices for multi-polygons, so sets of these guys. And then it's a list of anything of the above for these guys. Yeah, so any type we say set, we use list. Anytime we say point set, we use matrix. I can understand if that is kind of, sounds abstract to you, but whatever, if you would do it, I couldn't think of a simpler way of actually doing that. So, although somebody commented that a point should be a matrix with one row, but then I went like, oh yeah, well, hasn't harmed us so far. There is this convention that all the SF functions, or practically all, there is a couple that don't, but practically all the useful functions basically start with st underscore, and that helps, and that we sort of took the convention that always the first argument is sort of the argument you work on, and that helps when you work with pipes. Yeah? So not everyone works with pipes, but it is easy. There is also like a couple of functions that have aliases. So there's an stRead, which does, which reads things. We can stRead. Let's just look up an example. Here is the canonical example of reading a shapefile. We can also read an GeoPackage, which is of course better. GeoPackage file. So we're now reading a data set, a North Carolina data set from the package sources itself. Yeah, so this works for everyone because this is a data set that comes with a package. That is why you see system file. So I have a completely different file system than somebody working with a Windows or with a Mac. This is something that always works. I'm now reading this, and you get this long report telling where it was read from, so you can read this is where it was read from. That will not work for you. This only works for me. This is why it's resolved like this. And it gives a little report, a summary of what it does. And then what I get is an object of class SF data frame. So it's an SF data frame. So it's still a data frame, but it's of type SF. Yeah, so that there are a couple of methods like print and so, which are different from the standard data frame print. Standard data frame would print all the records. The SF data frame, SF print only prints the first 10 records here. So we see here the first 10 features printed, which is kind of copied from Tibble stuff. An alternative would be to use, instead of stRead, to read SF, read underscore SF. The read underscore something is more what the tidyverse does. Like has the package readr has things like read underscore CSV and read underscore something. And this also does this, and this is silent, yeah, so it doesn't do anything, and it's not only silent, but it also reads it in as a tibble, as an SF tibble. So you can see here that what I now get is sort of an SF object that is still a data frame, but it is also a tibble. Tibble are the sort of the better between quotes data frames that Tidyverse uses. Nice thing about that is they have slightly more elaborate print methods, right? So still SF sort of glues this little header on top of it, but then we basically get the tibble printing of the sort of the rest, and you can see here that it does things like abbreviating columns and all kind of fancy things with colored fonts and so on, and it's very nice, yeah. I like it. Some aspects. Yes?
Many people come and know Tibble. Why is it called Tibble?
Tibble. Sounds good.
Yes, there is no really such thing as
Tibble, I think it's called Tibble because it sounds good.
Is it because the abbreviation TBL?
Table, right, it's TBL, and if you say TBL fast, then it sounds like Tibble, right? You have to say Tibble. Yeah, no, I don't know. Good. The reference systems is a sort of important part of this whole thing because we have coordinates, as I mentioned yesterday, and for coordinates it's important to know where they came from and what they refer to, yes? The most important distinction here is whether your coordinates are geodesic/geographic or whether they are Cartesian. Yes, geographic is let long, and if they are let long, are they let long or long let? What is the long? What's the let? Right? That is not sort of automatic, but that needs to be sort of cleared out. They have a unit, yes. Even if they are longitude latitude, they could be in radians. In principle, it's of course conventional that they are in decimal degrees. And what is also important, if there is a datum, that you have information about the datum. So longitude, latitude measured along which model of the Earth? Yeah, is this WGS84 the global one of the global datums, or for instance the European terrestrial reference system, or for instance some North American datum that definitely different from WGS84. Otherwise, you have projected coordinates, like things like UTM, Web Mercator, and they also have a measurement unit, and sort of a lot of these projected things in the US or UK will have feet as units and so on. So this is important when you want to sort of relate one thing to the other. A third option that I don't mention is that you can have sort of a not geo, not Earth related reference system. That is, if you are, for instance, if you do, you do measurements on your medical doctor and you do measurements with a CT scan on sort of locations of tumors in the liver of your patient, then you have like three-dimensional coordinates, but it's not like, it's not like they're, of course they have an Earth reference the moment you measure them, but that is not so interesting. Yes, the interesting thing is sort of where in the patient is this, right? How large is the liver and where is the liver, and sort of how do you, so you take the body as a reference system, yeah? So that's another one. If the patient would move, your Earth coordinates would move, and that is not interesting. The thing is which part of the liver is actually infected or is diseased. So those are kind of custom coordinates, and a lot of spatial data is, of course, is in that sense custom, or is sort of not Earth, where the Earth relation is not relevant, is either moving or it's sort of transient, or for instance, you're looking at microsections under the microscope, right? You're also measuring things and so on, and drawing polygons on your microscope images, and you're not going to sort of do that in longitude, latitude, right? You're using a local coordinate system. So in that case, you say the coordinate reference system is simply missing, and that means it's assumed to be Euclidean. Yes, in that case, the missing coordinate reference system will be assumed to be Cartesian. So we have a function stcrs, and stcrs creates an object of class CRS, and that is a coordinate reference system. Yes, a coordinate reference system, in any case, have a string that describes this, and this is sort of the string that's understood by proj4, which is now called proj. And many of them also have a number, yes, a number that refers to a data set of, let's say, agreed coordinate reference systems, there where, for instance, 4326 is longitude, latitude in the datum WGS84. And not all of them have that. Yeah, so you can define your custom projections with particular parameters. There's infinitely many of those with these strings with numbers in them, and a lot of things like national. Whenever you have the Czech geodetic society will do its mapping in a certain reference system, and will have a certain number for sort of the reference system they use to do that. One that is often used is 3857, that is the web Mercator one, and you can sort of query the units of these things by these kind of operations. Yeah. So here we have meters, 4326 will have, oh, it's interesting, has no units. So there is no units in this string. So there is a unit string here somewhere in this proj4 string units is meters. And then here, if we ask the units component, it will basically parse the string and sort of draw out this units component. So now we're going to do something with real data. We already read that. We already did that. So we're going to read here from we're going to read a shapefile from the package with readsf. And then we're going to print the first 3 records. And you can see here we only see a couple of variables. We don't see all the variables. It says it has 97 more rows. So in total 100 features and 5 more variables. And here the name of the variables. And then we plotted, and when we plotted, there's the default plot method that essentially says, okay, I'm going to, well, the default plot method is to plot all the maps. But then if you have like 100 or 500 so all the maps in the sense of all the variables. Yeah, so every variable is an attribute, is something that you could display on these polygons, and that is what it tries. But then it will stop after like 10 or so. So I can also say plot nc max.plot is 2 and are 4, and then I get 4 of them, and it gives me 4 of them, right? And it will sort of try to sort out, try to sort of find a suitable layout that your plot area is filled. And of course you can't, it doesn't display legend because these are all completely different things. The area variable, by the way, is completely false in this data set. Yeah. It is area computed from degrees, latitude, longitude, as if they were Cartesian coordinates, interestingly. Yeah, so, and there's no help, I think, with this data set, no. So this is a way, and you see the different color schemes that categorical variables, so factors, use a categorical data scheme, and everything else, numerical variables, get a continuous data scheme, color scheme that you can modify. So we can do things with this, and for instance, we can use ST transform to go from one coordinate reference system to another. Yeah, this is a very important activity if you start working with spatial data. For instance, we can ask here what the area of the first county in North Carolina is. This is this many square meters, as you can see, but we can also convert this to another to a projected system, the North Carolina state plane with SI units, so with meters, and we see that it is different, so it has a slightly different area. So that is what happens basically if you have a polygon and you compute the area on the sphere. It gives you a different result. It's a different computation than when you sort of move that area to a flat plane, and from the same area, sort of the moved sort of the projected area, compute the area, you get something that is very similar, but that is not the same. So you can see here after the fourth digit, it starts to change. Yeah. Here we have the same projection, but then in US feet. So we get a completely different number, but also a completely different measurement unit, square US survey feet. And we can sort of convert these square feet to square kilometers, and we get this number. And that corresponds to the second one in square kilometers. So these two projections essentially do the same, exactly do the same up to the measurement units. Yeah, so it's this exactly identical projection. I forget what it was. I think Lambert conform conic or something like that. Let's ask. Yeah, LCC, that is Lambert conformal conic, so one of these conic projections. And you can see that it has the same parameters. If I ask for this one, you can see that all these parameters of specifying which conical shape you want to use for projecting are identical, and everything is the same up to the units argument, where we have here units is US feet, and here we have units is meter. And so we can do these things. This is so the state projection. This is standard, and then you can choose whether to work with US feet or with SI units, meters. And then from now on, I say we will work with the North Carolina data set that we transform. So we have transformed it, and we have sort of then here plotted in meters, and we can plot, for instance, the first variable, and then say x is true. And we get a plot, which was it? So we get this plot, and you can see here that along the axis, I get now these sort of these values of the coordinates that are sort of very large numbers, yeah, that represent the units in meters. Yeah, NC now has a different bounding box. You can see the bounding box now has values that no longer can represent angles. Yeah, they cannot represent latitude, longitude, because they're outside plus minus 90 for latitude. They're outside plus minus 180 for longitude. So we went to that projection. You can also see that I don't use RStudio a lot, because I just I might get there. Yeah, that it's a question like, okay, what can we do with simple features? And it is always hard, right? Because you can of course look at a package. Where is the package? Oh, the package is here. Then tell me what's in location. Oh, there's 116 functions there in the sort of in my second place on the search path. So there are 116 functions. There is more clever ways of finding out what are the methods for, which methods are there for an object of class SF. And there's quite a few. You can see that there are now 53 different methods available for them. This is a very or if not an extremely primitive way of finding out what there is, although the methods command is pretty powerful. Another way that I could recommend you is to go to the cron page for, cron of course has the reference manuals, right? You may have seen these things, but they're also not, they're long, wow, 84 pages, and they're just a list of the whole documentation printed to a PDF. Yeah, so they're not very, very friendly. A more friendly interface to all this documentation is actually found if you go to it's provided or can be created by the package down, derived from markdown and so on. If you would go to the GitHub side of the SF package, which is basically the URL here, so you GitHub Spatial SF, Then you will find simple features for R, and then it has this link here at the top. Yeah, you can see, there is rspatial.github.io/sf, which is the documentation, which is basically the same thing. It contains it contains the README, it contains the reference for the functions, and it contains the 6 vignettes, but in a somewhat more sort of organized way. And the reference, for instance, gives you all the functions and gives you pages for all the functions, but also if you click on one of these things, then you also see directly that you see the examples being run, and you see the figures of the output from the examples actually inserted in the section. So this is a way more friendly way of reading our documentation. Yes, that is not integrated in cron, regrettably. Maybe they will someday, but a lot of packages actually do this. If you would go to, the ggplot site on tidyverse, you will also see that the same thing, that you have the references and you plot and you print. So if you click on anything and you get sort of examples with figures inlined, right? So this is also a product from Hadley Wickham to make our documentation better accessible, more readable. As I mentioned, there's a couple of low-level I/O stuff, so you can convert to well-known binary to well-known text, convert back from all kind of things. There is an interesting one that we didn't discuss yesterday, but there is an as method to convert an object X into a spatial object. Yes. And there is the other way around, ST as SF. And these two are kind of right now, because a lot of stuff still goes on with SP and packages that need SP stuff. And whenever you work with simple features, you want to do something with a package that assumes that your data come as SP objects. So you're torn, right? What shall I do? Well, the only thing you have to do is as spatial. Yeah? So I have this NC object here. And if I say nc.sp is as nc, spatial, that's all. Yeah. So nc.sp is now a spatial polygons data frame. Yeah? It's that simple. So no magic going on. And the other way around is nc2 is then st as sf from nc.sp. Is the other way around, and I obtain an SF data frame and not a tibblback, right? Because I lost the information on my way that this was made from a tibble. Yeah, but you get back an SF object. So this is not. So this is very convenient, and this will probably work in 99.9% of your problems. But I should mention here that. Not everything, sort of that a simple feature model is more sort of comprehensive than the things that SP allows. Yeah, SP has points, lines, and polygons. But if we look at it into detail, then the SP lines and polygons are really multi-lines and multi-polygons. Yeah, so if I have something that is line string in SF and I move it to SP, it comes back, it will be a multi-line string, probably, yes? Because that information is lost. Yeah, whether something is a line string or a multi-line string of size 1, it doesn't make that distinction. SP just says, well, polygons can be polygons, one or more polygons, right? Essentially meaning multi-polygons. So there is only the multivariance. There is not much of a multi-points implementation. There's nothing like geometry collections. Yeah, so if you have geometry collection, it doesn't map. Yeah, there is no similar thing in SP. Good, but this is useful. Then there is logical binary geometry predicates. and those things those things basically look at, so they're binary predicates. They look at combinations of geometries, so pairs of geometries, and look at whether they have a certain relationship. Yeah, so the most general is ST intersects. Yeah, so do A and B intersect? Yeah, that is the question, and that leads to an answer yes or no, essentially. Yes, that means they touch or overlap, essentially. So they have something in common, whatever it is, whether it's a point, a line, or an area. They have something in common. ST disjoint means that they don't intersect. Yeah, so this is the reverse. ST touches means that they touch, that they intersect. I think it means that they intersect, but that the intersection is not an area. Yeah? That they intersect either in a line or in a point. Yeah? So two polygons touching each other means that they intersect but do not partially overlap. Yeah? And then there's crosses and so on within, and contained in all these predicates, and there is covered by, and then you think, oh, but what do they exactly mean? Yes? And what do they exactly mean? You can figure that out. Let's do that first, because I never know. Dimension E9. So the model it uses for that is the so-called dimension extend 9 intersection model. The E9IM is a topological model and a standard used to describe the spatial relations of two regions or two geometries in two dimensions. Yes, what it really does is sort of, it looks at, so it's a binary operation. So it really says, every geometry we have, we can think of it having an inside, having a boundary, and having an outside. For polygons, this is easy, right? It has an inside, it has a boundary, and it has an outside. For points or lines, it's a little bit more abstract because you think, well, what's the difference for a point between the inside and the boundary? But it doesn't really that doesn't really matter so much. But what it does really, dimension the 9IM sort of looks at two geometries. Let me see if there's a better figure here. Yeah, looks at two geometries A and B. It looks at the interior boundary and the exterior, and then it looks at the dimension of the intersection of these two things. Yeah, so there is, since we have three properties, interior, boundary, exterior of A and 3 of B, we can make 9 combinations. Yes. So here we look at the red area. How is the interior of A and the interior of B related? Well, it's an area, they overlap, so that has dimension 2. How is the boundary of, how is the interior of A, the blue area, related to the boundary of B? Well, that's a line, this boundary, so that has dimension 1, and so on, right? And we can look at both boundaries and look at both exteriors, and so we get 9 combinations, and all these 9 combinations have a dimension, and the dimension can be 0 for a point, yeah, can be 1 for a line, can be 2 for an area, or it can be none, yes, if there's no relation between the two. So if A and B would not intersect, then their interiors would have would have a false here. So, and then from that, we basically create a string. We sort of collate these 9 numbers, and we get this string, which in this case is 212, 212, 101, 212, and that is basically an encoding of these 9 relationships. Yes, where we sort of go row by row. So it is this, 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 this is this, and this is this. Yeah. The example is a bit unlucky because it is either way. You would, if you would do it column by column, you would sort of get the same string. And that pretty much gives you all the possibilities of intersections, or everything that we can currently think of. And now comes the fun thing, is that all these predicates we have, equals, disjoint, touches, contains, covers, and so on, can be expressed as encodings in terms of these strings of nine symbols. Yeah. Now you see this looks a little bit different than this one. These were the sort of dimensions, and here we see true, star, false. True means either 0, 1, or 2. Stars means doesn't matter. False means no intersection. Yeah, so neither 0, no 1, no 2, no intersection. Yes. And so we have the equals predicate expressed here as this string. So if we have this string basically coming out of doing the DE9IM analysis, then we have two geometries that are identical, yes, that are equal. And the fun thing is that that means they are topologically identical, because you would say if I have two polygons, well, you know, it would be pretty easy to find out whether they are identical, because I could just check the coordinates, right? But it's not so easy, because one polygon might start here and the other polygon might start there. So it's really about the region that they sort of span than about the order of the coordinates. Yes? And that is what this does. So it does really the topological relationship rather than some kind of numerical analysis. And this is a very powerful thing, not just because you can, by this you can essentially find out what all these predicates really mean in terms of what intersects in which way with which other things. But you can also go a little step further and define your own predicates, which we will do next. So this is going on under the hood. Here is just to show what happens. Here I took the first 5 counties from NC just to make the output a little bit smaller, and I computed the intersection of this subset of 5 with this subset of 5, and then we get back a thing that looks a little bit odd, and it is a little bit odd, but it's not too bad. It's intentionally. Yes. So we get an object back called I, which has a class and has a print method, and it is an object of class SGBP, so that stands for Sparse Geometry Binary Predicate. Roger and I have been thinking a long time about how shall we call this thing, and it's dreadful. Yes, it's a terrible sort of. I can never remember in which order the sort of the characters come, but it's a sparse geometry binary predicate. If you say it a lot, it says if it prints here, oh, it's a sparse geometry binary predicate, and it's a list. Yes, the main thing is it's a list, and it is the length of the list is the length of the first argument. Yes. And every list element, so the first list element, basically is a vector with the indexes of the elements of the second element, the second argument, with which I have intersections. Yeah, so the second element of the list is 1, 2, 3. The fourth element of the list is 4. So they're just integer vectors. Yeah? They're indexes. The reason why we do it this way, the other thing you could do is, well, why don't you make a Boolean matrix, right, from n by n, and you can get this thing by saying as matrix, you get a Boolean matrix where you say, well, here are the elements of the first argument x, here with the second argument, and then I can look at all the combinations and see true, false, whether I have this, you know, it's a Boolean predicate, whether I have an intersection or not. That would be easy enough. The thing is, if you have a lot of geometries, right, and mean a lot of them, like 100,000 or so, or a million, then giving this Boolean matrix would sort of has n-square storage, right? You get a matrix of 1,000,000 by 1,000,000 elements, and you probably don't want that. That is one reason. The other reason is that this matrix is very sparse. It's mostly filled with falses, right? Because things only intersect with their neighborhoods, right? There's typically, you know, a point that typically falls in one polygon or something like that, right? So it's full with falses, and that is what this object basically prevents. So it directly gives you a list with the indexes, and you can convert it to a Boolean matrix if you find that easier. And it has a class so that it only prints the first 10 elements, and it prints it in a kind of a sort of a neater way. Yes. The unneat way would be unclass I. It would be print something like this, which is not very nice. Yeah. Right. So let me see where I can. That was a little bit further on where I was doing that. Yeah. So this is intersection. Then we have geometry generating logical operations. They're not. So they're geometry generating operate. They're not logical. Sorry, this is a mistake. So union, intersection, difference, and sim difference create new geometries from pairs or larger sets. Yeah, so as the union sort of merges two things, it's the intersection, computes the intersection, returns the intersection as the geometry of the intersection. Yeah? So there's a very strong difference, large difference between ST intersects, which is basically a question mark, gives a Boolean answer, or ST intersection, which computes a geometry. Yes, it returns a geometry. So if you want to know whether two things intersect, you ask ST intersects, question mark. If you want to compute the intersection, you ask for question ST intersection, which is an intersection, which is a geometry. Difference does a similar thing. It computes a difference, so, and sim difference, it's the symmetric difference. I think that there is some... So this is the... Yeah, this is... here we see, so this is... If we have two circles, this is the union, this is the difference, A minus B, this is their intersection, and this is their symmetric difference. Yeah, we can do these things. But this is then also encoded as, let's say, as expressions, which you can also do. So what we do here is computing a buffer. We see that we computed the we have the sort of the North Carolina geometry. So with ST geometry, we pulled out the geometry column. So we have a geometry column in this here in this object. And we computed here the intersection of the first and the second county. There's those two countries. We plotted it here as a red line. So we see this is the intersection. It's a line. They don't overlap. And we computed a buffer with 10 kilometers and said this is blue. So this is the area around these three states. And then it's cut off because this sort of extends the plot region. So it's a full polygon, but it's not fully plotted. It is just because I plotted the black area, the three states, that sort of limits my plot extent. So we don't see the full blue polygon. It is cut off by the extensions of the plot. And we can do negative buffers, and negative buffers basically means that you shrink something, right? That you don't extend the region, but that you shrink to it. So you get sort of the smaller area that kind of the area that is further inside the three counties, but further away than 5 kilometers from the nearest boundary or something like that. Yeah, those are the kind of things that buffers do. So buffers is another way of computing new geometries based on old geometries, right? By extending or shrinking areas. There is a funny thing that we have sort of implemented relatively recently in SF, that is intersections and differences that you do on higher order. Let's say we have now looked at unary operations, yes, so operations on single geometries. We have looked at binary operations, so operations on pairs of geometries. Do they intersect? All these kind of questions. Do they overlap? Or what is their intersection? But now there's a question like, what do we do with three? Yes, or what do we do with three or more geometries? So think the use case that I could have in mind. This actually came out of an interesting question on Stack Overflow, where somebody said, I have all these regions which are the distributions of particular species, and now I want to find out sort of all the unique polygons by sort of intersections of all these things. Yeah, sort of find out for each polygon how many species live there. And if you can only do like species A with species B, and then species C with species A and with species B, then you don't have the area where A, B, and C, all three occur, right? So doing that sort of from the pairwise operations is an incredibly complicated thing. So you would like to do this in a sort of higher order setting, and we sort of figured out how to do that, and that is shown here. And that happens if you call ST intersection or ST difference with a single argument. Then it will go through the set and do the higher order intersections. And this is an example where I just generated random squares and gave them sort of random colors. You can see here that that they are plotted with an alpha level. Yeah, so you can the colors are translucent. Yeah, so you see mixed colors when they are plotted on top of each other. So these really squares, and we have lots of overlaps in certain areas of these squares. So what we can then do is here, for instance, we did a difference. So this is the sequential difference. That means we get the first square, we get the second square minus the first square, we get the third square minus the second minus the first, we get the fourth minus the third minus the second minus the first, and so on. So it's sort of sequential differences. Yeah, they're not pairwise difference, they're higher order differences. So the last square we get sort of subtracts all of the previous squares. Yeah, and then what we get is non-overlapping squares. We see they're still plotted with the same alpha level, but we don't see any overlapping colors anymore. Right? We would have seen that when plotted on top of each other with an alpha level with transparent colors. Yeah, to just stress that we can compute the overlaps, and we can say what was it, the D here? Yeah. So we have the sequential differences. We can analyze these and say how much do they overlap, and then you can see there are no overlaps of these sequential differences. And the other thing is that we can get non-overlapping intersections. That means that we get sort of all unique combinations, that we get sort of all polygons that are formed by overlaps from other polygons, but potentially from more than one polygon. Yeah? They're plotted here. This is a little bit of an intricate plot. You can see because the color scheme kind of rotates, we don't have so many colors. But you can also say that they don't overlap. And what that command also does, ST intersection, is that it adds two fields. If my object is an SF object, it adds two fields to the new set, and the field is the number of overlapping things. So we can see here how many original squares do overlap for each of the new generated polygons, and we also get which of them overlap, I think. ST intersection. Yeah, so I get these plots that we just saw, but we also see that this I thing does not only have a field n overlaps, but it also, for each new polygon we get, it says, what are the origins? And you can see that this is a list column, right? This is, again, a column that has indexes, that can have multiple indexes, because that points back to which of the original. So if I have an area where 200 species occur, yeah, because so many of these polygons overlap, then I can get in these origins, I can sort of find out which 200 species are these. I get them back. Yeah. So this is a nifty thing that you can do with ST, with package SF. And that is sort of convenient to have. Where is I? Right, then we go to higher level operations, summarize, interpolate, aggregate, and ST join. the aggregate is, who of you has ever used the function aggregate? Yeah, good, good. So that is like 15%. Who of you has ever used the function summarize? Okay, that's a little bit more, but like 20% or 25%. Yeah, so aggregate and summarize are two generics, aggregate from base R and summarize from dplyr, I think. They summarize stuff, so they summarize records, really. And they have methods for SF objects, and what SF does is that it really sort of, when it summarizes features, it also generates the new feature geometry by calling stunion, yes, by default. So this is basically what happens. That is an easy thing to do and convenient. More interesting thing is the function st_interpolate AW, which stands for area-weighted interpolation. And this is the problem that we pretty often face if we have, let's say, polygon data, one set of polygons, and we want to go to another set of polygons, but they don't nicely line up. Yeah, so summarize and aggregate would just put polygons together, right? So I want to sort of put these 3 polygons together and these 5 polygons together for some reason and get a new polygon that is formed by their union, right? So there is no cutting up, there is just merging of geometries. Yeah, this is a relatively simple thing. But what if these sort of the target areas don't really line up with the source areas? So we see an example here where we have the North Carolina data set and we have a new sort of polygon layout, so which looks like a raster, but which is really a set of polygons that is sort of laid out over these areas. And I want to sort of have this variable, birth rates in 1974. I want to have estimates of that for these new polygons, yeah, for some reason. Yeah? So this is what we call, well, whatever it is, regridding, downscaling, upscaling. It is kind of the messy, the messy aggregation where things don't line up. And the simplest thing there you can do is say, well, of course, if these are, the real thing you have to do is say, well, we can't do this because this is about number of people, and people live somewhere, and we don't know where they live. We only know how many live in the polygon. So if we would do something for a new polygon, we can't do it. Yeah, so that would be the sort of the honest answer. Yeah, and then comes your chef and says, I want you to do this, right? Because I need a result and so on, I need it by tomorrow afternoon. And so you start thinking, okay, what can I do? So this is the dreadful thing about data science. What you can do, the simplest thing to do is basically say, well, suppose they're evenly distributed. Yes, so they live everywhere and they're kind of constant density. And if you do that, then you could say, okay, it's constant density. So I have a new area which doesn't line up with old polygons, but I have the old polygons, the intersections, and I can look at the densities, and I can kind of area weight that. Yeah, so there is a small area with high density, large area with low density, and then another area with extremely high density, and that kind of weighs out by you can compute the new densities for that. Doing that, there is 2 things that you need to sort of think about. And first one is whether you have an intensive or an extensive variable. So is anyone familiar with intensive and extensive variables? Yes, go ahead. What was? So do I. Yes.
I've seen this representation in another Jews that, and you explained that. That was the last time I...
Okay. So I explained it to you 2 years ago.
Yeah.
All right. Go
Yeah,
ahead.
probably. I think intensive, when you split it in 2 pieces, that characteristic stays the same.
Yeah.
And extensive is not, is like weight and the intensity of a stone or something. When you cut it in half, the
Right.
intensity doesn't change, but the weight changes.
Right. So that is the difference. So you have something, you cut it in 2, does the value change, right? For mass it will, for volume it will, but for temperature it will not, and for density it will also not, right? So, and that is the same thing here. Do I work with population densities, which is kind of intensive, right? If you take a smaller area, it's a similar number. Yeah, that this we say it's everywhere the same. If we say this is number of people, then if we cut the area in two, we have suddenly half of the number, right? So we need to decide which we do. So we can do area weighted one way or the other, and there is no in between. There is just a binary split. And that is why this function, as the interpolate area weighted, has an argument extensive that needs to be set. Yes, so the function doesn't work if you don't set it. Yes, because it has to be one or the other, so it's true or false. And you can do both, and I did here both, and of course one is wrong. You can see that the answers are pretty much different in terms of where sort of the higher values allocated. The good one should be this one. We can check basically. So we did we area weighted interpolated this birth 74 variable from this source geometry to this target geometry. This is the sort of comes out of estimate grid, so that makes a grid of polygons over the region. So this is the target geometry, and we say extensive is false. So A1 is extensive, A1 is intensive, A2 is extensive, and we can look at whether the total number still matches, right? And we say that for A2, the sum over the division of the sum over the original sum is 1, whereas for intensive, the sum over the original sum is 1.4. So we end up with much more population in the intensive case. Yeah? So this case, we didn't redistribute, we generated a lot more people than there were originally. In this case, we redistributed people, but we kept the same amount of people. Yeah, so this is two things you can do. So this is really going from one to another, and then there is a lot more you can do, a lot more methods that you can use for doing this in the proper way. So proper way would use covariates. The key word is asymmetric mapping. So basically finding out where people live based on all kind of land use characteristics. So you know totals for cities and so on. And you have high density land use maps, and then you want to sort of get high density population density maps, and then it's called asymmetric mapping. So there's much more to do to this topic than there is here, but this is kind of a thing you can do. And the fun thing is that the function is only 20 lines. Yes. But I must say it's 20 lines, and I went back to it twice, and I didn't understand anything of it. So this is one of these dreadful things that seem to work, but you always hope to never have to revisit it again. One of the reasons being that I always forget what is extensive, what is intensive. Anyway, another function you have is stjoin, which basically merges two tables based on spatial predicates, as I said. So I could, for instance, want to find the county that matches a certain coordinate. He would be the coordinate. This is sort of, creating the geometry column, list column, yeah, creating the SF object. And here I am joining them, and this is stjoin. So it joins them on spatial correspondence, right? And then what I get out is a single observation, which has all the attributes of the sort of the North Carolina county, spatially corresponding, so intersecting with this newly point that I defined here. So it's like a point query that I do. There you need to be aware that stjoin actually has a join function, so you need to define what the predicate will be to join records. Yeah, that is by default st_intersects, but it could be like contains, right? If the point would be on a county boundary, I would get 2 matching records. Yeah, there would be 2 matching boundaries if this is a boundary, or more of them. And I could also say contains or something like that, and then that corner case would be dropped. Yeah? So this is flexible, and you can write your own functions there to get more elaborate. Yeah, well, it's basically what it does. So you do a table join based on a spatial join metric. Yeah. So if it intersects, then you get, for this point, you get back the records on the other table, all the properties of the other table that correspond, that intersect with that point. Yeah. Yeah, here we do a join with itself, so we get direct neighbors, but we get also the state. So self joins we also get. We can also see how often we get touches. That is, of course, 100 times less. Yeah, now we don't have intersect. We don't have self intersections anymore because every state touches its neighbor states, but it doesn't touch itself. Yeah, so we get 100 less. And this is a little exercise I did when I looked sort of at these polygons of North Carolina. You see this funny thing that, you know, it looked like here, it looked like somebody went there, right? And just drew the map by drawing horizontal and vertical lines and sort of created counties that way. Yeah, that's probably what happened. And it is one of these things that in Europe that we're not so familiar with, that we have places where 4 administrative areas actually touch. Yeah, because we have, you know, all our boundaries are the result of 700 years of war, typically, yeah, especially in Germany, and so we don't have it. So the question here, what I wanted to do is sort of where are all these points where 4 counties match? Yeah, so that is a question that you could ask. That is, you know, sort of spatial analysis question. And there you have to ask basically where do I have, you know, so ST touches doesn't do that, because touches means they can touch in a line or in a point. So what I really want here is basically places where one state touches another in a point rather than in a line. Yes, and I did that by using the ST-relate. And ST-relate is basically the generalizer of all these predicates that takes a pattern, yeah, where you say, well, here is this pattern. So if I would say ST-relate with the equal pattern, then I get ST equals. Yeah? So this is sort of the meta function that does all this with the D9IM magic. And it can sort of create a function, you know, find my rook neighbors. So rook neighbors are neighbors that only touch in a point, and do that by defining a rook function that calls ST-relate with this pattern. Yeah, so I have my new predicate function here defined, and it can say, well, join with ST-rook, and then it plots all the geometries where this happens. This came up, by the way, by somebody else who sort of raised an issue on a similar thing on the Martin Tiernan, who raised this thing on the SF GitHub page. And this is sort of a way to find the points where this happens. Yes? Yeah. So here I sort of get all the intersections of states, so including all the self-intersections. And here I get all the intersections elements. So these intersections are now area self-intersections. They are lines of boundaries, but there are also points where for instance, this state touches that state. So I'm now selecting all the intersections that have dimension 0, so that are really points, and adding them. So you can find these points and add them to this plot. Good. So far, we have 5 minutes before lunch. So I can see on my progress bar that I'm sort of over half of my material. That doesn't mean that the second half is as light, second third is as light as the first half. What I do have in mind is actually to have you think about, let you do some exercises, and I don't want to sort of leave the room here before sort of showing you these exercises. They are all at the end, they're completely at the end of this document. And the exercises use data with permission from the package map view. The package map view contains a couple of data sets. Breweries, the point locations of the set of breweries in Franconia. Trails, a set of hiking trails in Franconia, and the administrative regions in Franconia. So we have points, lines, and polygons, and we're going to do some, some tough things with them, yeah, or some light things. So I try to start with very light exercises, and yeah, for each of the data sites, describe the geometry type, try to find the data and see if you can understand it and find the results, and then plot each of these three things to see what's going on. Then try to export this polygon data set to a geo package, which is a nice exercise to try to have tried once and load it in quantum GIS, see what happens there. Compare their coordinate reference systems, yeah, because they turn out to be not equal, and then decide what to do, because we want to do combinations of these three data sets. So let's deal with that first before sort of combining them raises all kind of errors, because this is not automatic. And then we get the combination questions, like for each of the trails, find out which brewery is closest to the trail. For each of the trail, find out the distance to the closest brewery, important things. For each of the trail, find out how many breweries it has less than 500 meters away from the trail, per kilometer of trail. So like near brewery density or so. It's a good sort of summary statistic to describe these trails. For each of the regions in Franconia, find out how many breweries it contains and add this number as a field to the Franconia object. And for each region in Franconia, count the total number of types of beers brewed by the breweries in the region. Yeah, so these are kind of the summary statistics things of points and polygons, and then the lines and polygons count the total length of trails per region in the Franconia dataset. So these are kind of intro to GIS, intro to spatial analysis type of questions that we can basically now do. I would like to spend let's say the second half of the second part of the morning session on trying to do that. So I tried to come up with a question first, and then I tried to do it, and it took me actually a lot of time. So it was not at all easy. But yeah, I don't do these things daily, but it's anyway, it's fun. So are there any questions right now? Good. Is there any persons who could sort of, while I was going through stuff, could actually do some commands with R that I tried out? That sort of, who of you were sort of actively trying out things with R that were on the slides? Yeah. Okay. Good. That is like 15% or so. Good. Thank you. Okay. Then we'll have a coffee break now, and we'll continue in like half an hour. Thank you.